In this video, I am going to discuss about uh, parallel plate capacitors or parallel plate conductors. Generally, the problems that are given is that we have some conductors or parallel plate capacitors, and initially some charges are given on the plates like Q. In this problem, it is given as Q and minus 2Q. It may be any, and the third plate is not having any charge, but in general, any kind of charges are initially given to the plates, and we have to calculate the charges which appears on the faces of the plate, that is on this face or the other faces. The charges appears on the faces because electric field inside the conductor has to be zero, so they have to appear on the faces of the plates. Likewise, we have to calculate electric field or potential difference between these two. For example, we have to calculate electric field over between these two plates or potential difference between these two plates. Sometimes the problems are given in such a way that some of the plates are connected to a battery. For example, in this case, a battery is connected to plate A and plate B, or in this case, plate 2 and 3 are connected to a plate 2 is connected to a positive terminal of the battery, and plate 3 is connected to negative terminal, and the other plates are joined together. So and in this case also we have to find sometimes equivalent capacitance and or electric field or potential difference between the plates. So overall, these kinds of problem can be solved on three basic theories, three fundamental concepts we can say, on which these problems are based. So I will discuss those problems one by one, and particularly in this video I have discussed the theories and the formulas that are related to finding the charges on the capacitors, and in the next video I have discussed to find the electric field or potential difference between the plates, and in subsequent videos I have discussed problems related to these theories. So I will start one by one. Fundamentally, there are three concepts that are related to such kind of problems. First one is conservation of charges. So if there is an isolated conductor, so total charge on that conductor remains same or it remains conserved. Second is based on Gauss law, and third is that the electric field inside a conductor is zero. So let us consider this parallel plate capacitor or a conductor which are initially given charges Q1 and Q2. So this Q1 is the total charge which is on the plate 1. Suppose this is our plate 1, and Q2 is the total charge given to plate 2. This is our plate 2. Now if these plates are joined by a conducting wire, they together constitute an isolated conductor, and although the charges will appear different values on different faces, but the total charge on these two conductors will remain same, that is Q1 plus Q2 will remain same. Now suppose this is our conductor 1 and conductor 2, and they are connected with a conducting wire. For the sake of convenience, I have labeled the faces. That is, on first conductor, the left face is labeled as F1L and right face is labeled as F1R. Similarly, for second conductor, the left face is labeled as F2L and the right face is labeled as F2R. Throughout my video, this notation will be followed, that is F1L, F1R, F2L and F2R, and also notice that the left one is indicated with red and the right one is indicated with this green color. Now charges appearing on F1L is QA and on F1R is QB. Charges will distribute among themselves so that the net charge on F1L is QA and F1R is QB. Similarly, on F2L it is QC and F2R it is QD. Now, if we consider plate 1 and 2 and they are connected by a conducting wire, so plate 1 and 2, now they together constitute an isolated conductor. Therefore, the net charge on them remains constant, that is QA plus QB plus QC plus QD. This remains constant, and that equals to initial charges which were on the plates, that is Q1 plus Q2. This is our first fundamental concept, that the total charge on an isolated conductor remains constant. Second is based on Gauss law. So now suppose we have two conductor, parallel plate conductor, and they are having charges on F1L it is Q1, on F1R it is Q2. Similarly on F2L it is Q3, and F2R it is Q4. And I have considered any point P on the second conductor, so it is within the conductor, and within this conductor at point P the electric field will be 0. Similarly, if we consider any point over here, then electric field within this conductor should also be 0. So now consider a Gaussian surface. This green box is our Gaussian surface, and notice that the electric field between these two parallel plate capacitor or conductor will be along line joining, will be along positive x-axis. I have indicated this direction as positive x, and this is our positive y, this is our positive z, this is our right-handed coordinate system. So between these two plates the electric field will be along positive x direction. I have assumed Q1, Q2, Q3, Q4 all as positive, and these are simple notations. In actual practice, whatever be the charge, according to this the direction of electric field will be either along positive x-axis or negative x-axis, but it will remain along x-axis. And another point that has to be noticed is that each face, it behaves like a sheet. So this will have this face F1R will behave like a sheet. Similarly, F1L will behave like a sheet. Likewise, F2L and F2R will also behave like a sheet, and their electric field can be calculated, electric field or potential difference or anything. They will follow the same formula which is available for sheet, that is a conducting sheet. So now we have electric field in positive x direction, and if we consider the Gaussian surface, the Gauss law says that E dot ds is equals to total charge enclosed divided by epsilon naught. So E in this case is in positive x direction. Now we have to find the value of E dot ds for each surface. So for the top surface, ds is along z direction or positive z direction, so E dot ds will be 0. Similarly on bottom, the normal direction or the area vector is in downward z direction, so E dot ds is again 0 because electric field is in positive x direction. Similarly on the backward face, the ds will be along positive y direction, so again this E dot ds will be 0. And for this front face, uh, outward normal is along negative y direction, so E dot ds is again 0. Now in the rightward face, which is our this face, let us consider this as we are considering this rightward face. So this face, outward normal is along this green arrow is our outward normal, it is along positive x direction, but the electric field, I have considered this pillbox or the box Gaussian surface is passing through the conductor. So since electric field within the conductor is 0, so in this case E dot ds is again 0. This is not because E and ds are perpendicular, but because E is 0. Similarly on this left face, that is electric outward normal is along negative x direction, but again in this case the surface of the Gaussian surface is passing through the conductor, so because electric field is 0, therefore E dot ds is 0. So net electric field E dot ds, that is our electric flux, is 0. So we can say that Q, total charge enclosed within this conductor, is 0. So finally we observe that Q2 plus Q3 equals to 0. The total charge enclosed is this one is on Q2 and this is Q3, so total charge enclosed is 0. So we can say that Q2 equals to minus Q3. This is very fundamental concept that will be used in our problem. Now consider the I have shown here four conductors, and initially each conductors are given charges Q1, Q2, Q3 and Q4, and the faces are labeled as F1L, F1R, F2L, F2R, likewise F3L, F3R, F4L and F4R. 1 represents the number of numbering of the conductor, and L and R are left and right face. Red is our left face and green is our right face. So now suppose a charge Q appears on our first conductor on the rightward direction, that is on F1R. So from Gauss law we have just discussed, it is on F2L it should be minus Q. Now this first plate is an isolated conductor which was initially given a charge Q1. So on the left face the charge that will appear is Q1 minus Q, so that total charge remains Q1. Similarly on the second conductor, if we are considering the second conductor over here, so net charge has to be Q2 because initially it was given a charge Q2 and it is an isolated conductor. So on the right face F2R it should be Q2 plus Q. And from Gauss law the charge appearing on F3L will be minus Q2 minus Q. And again, since this is our third plate, so this third plate is an isolated conductor, so total charge has to be equal to Q3. So in that case F3R will be Q3 plus Q2 plus Q. If we add these, then Q2 and minus Q2 and Q2 will cancel. Similarly minus Q and Q will cancel. So this is total charge will be Q3. Now from Gauss law on F4L the charge that will appear will be equal to minus times of the charge that is appearing on F3R. So this will be minus times Q3 minus Q2 minus Q, and since total charge on fourth plate has to be Q4, so this is our fourth plate, so on this fourth plate total charge has to be Q4. Therefore on F4R the charge that will appear is Q4 plus Q3 plus Q2 plus Q. Now if we add these two we will get, because fourth plate is also an isolated conductor, so total charge has to be Q4. So when we add these two, that is Q4 plus Q3 plus Q2 plus Q, and then minus Q3 minus Q2 and minus Q, so we will get a charge Q4 on fourth plate. Now let us consider four conductor that we have just discussed, and we have distributed the charges. I have just explained it. So on the left plate it is Q1 minus Q, on F1R it is Q, by Gauss law it is minus Q, and on F2R it is Q2 plus Q. Likewise we have just discussed all these charges. The fundamental concept used here is either Gauss law or the conservation of charges, and on that basis we have calculated the distribution of charges on all the faces. Now once if we notice that here that Q1 Q2 Q3 Q4 was initially given to the plate, so these are known, so only unknown is the small q. If we are able to calculate this small q, we can calculate all the charges that are appearing on various faces. So let us consider a point P over here on the fourth plate, which is inside this plate. This point P is inside the plate. So because of Q1 minus Q, there will be an electric field, that this is denoted by EP. I have denoted this net electric field EP. So because of q1 minus q, if we consider any positive test charge over here, let us consider a positive test charge. For the sake of visibility, I am showing the charge at upward position, but you can show anywhere. So this is our positive charge, and because of q1 minus q, what it will do, it will push the charge towards right. So electric field due to q1 minus q will be towards right. So I am writing this rightward direction as positive. So electric field due to q1 minus q will be q1 minus q divided by 2 epsilon naught. Similarly, because of q, this is our q, q will also push the positive charge towards right. This is our positive charge, so it will push the charge towards right. So electric field will be in rightward direction. So the magnitude of this value will be plus q divided by 2 epsilon naught. Plus sign is for the rightward direction. Similarly, for minus q, it will be in leftward direction because it will attract the positive charge toward itself. So the charge will try to move in leftward direction. So electric field will be minus q divided by 2 epsilon naught a. Likewise, for q2 plus q, it will push the charge towards right. So electric field will be q2 plus q divided by 2 epsilon naught into a. And I have assumed that all the plates have equal area, so the area is same for all the plates. Similarly, for minus q2 minus q, it will be towards left. It will attract the charge towards itself. So electric field will be minus times of q2 plus q divided by 2 epsilon naught a. Likewise, for q3 plus q2 plus q, the electric field will be towards right. It will push the charges towards right, and the electric field will be q3 plus q2 plus q divided by 2 epsilon naught a. Similarly, for this minus q3 minus q2 minus q, electric field will be towards left, and so the electric field magnitude of electric field will be minus times of the charge divided by 2 epsilon naught a. And for the last one, that is q4 plus q3 plus q2 plus q, this charge will push the positive charge towards left. So electric field will be in negative x direction, and its value will be minus times of q4 plus q3 plus q2 plus q divided by epsilon naught divided by 2 epsilon naught into a. Now this electric field EP has to be 0 because it is net electric field inside a conductor, which has to be 0. So this value has to be 0. Now notice that these are positive and negative, they will cancel out. Similarly, q2 plus q and minus times of q2 plus q, these two will cancel out. Likewise, this value and this value will cancel out. So we are left with net electric field as q1 minus q divided by 2 epsilon naught into a minus q4 minus q3 plus q2 plus q divided by 2 epsilon naught into a. So if we equate it, this is this equation we will get, and when we solve it, we get the value of q as q1 minus q2 minus q3 minus q4 divided by 2. This value we have just now calculated, and once this q is known, we can calculate q1 minus q. That when we substitute the value of small q and we subtract it from q1, we get q1 plus q2 plus q3 plus q4 divided by 2. Now this is very important result because this is the result which we will use to solve our problem, and this is a very interesting and very fundamental result. What it says is that the charge that is appearing on left face, extreme left, on its left side, that is on F1L, is sum of all charges divided by 2. This is valid for 3 plate, 4 plate, 2 plate, 5 plate, or any number of plates. So Qt is Q1 plus, I have used the symbol Qt for this left face, that is Qt is Q1 plus Q2 plus Q3 plus Q4 divided by 2. I am again reiterating that this is a very important result which will be subsequently used. Another important result that will come now is that when we calculate the charge on the extreme right, that is on F4R, on this plate, so the charge appearing on this plate is Q4 plus Q3 plus Q2 plus Q. So when we substitute the value of q over here, we get this expression. So finally it comes out that this value is also q1 plus q2 plus q3 plus q4 divided by 2. So what we are getting is that charges appearing on extreme left on its left face is sum of all charges divided by 2, and charges appearing on extreme right on its right face is also same, and it is q1 sum of all charges divided by 2. So this value, which was q4 plus q3 plus q2 plus q, equals to q sum of all charges divided by 2, which was equal to q1 minus q, which is the charge appearing on extreme left face, and that is same, and it is sum of all charges divided by 2. So these are the two results that we will use. And in my next video, in this video I have just calculated the charges which are appearing on various faces. The only unknown is the value of small q. Once this value of small q is known, we can calculate all the charges which are appearing on various faces. And the important result that comes out is that the charge on extreme faces, that is on extreme left on its left face and on extreme right on its right face, is same, and it is sum of charges divided by 2. Now for the sake of completeness, I have calculated the charge on the fourth plate, that is this one, and I have denoted the value. This is our fourth plate, and on this plate the charge on F4L is minus q3 minus q2 minus q. So, and I have denoted this value as minus qb. So if we substitute the value, we will obtain, there is a mistake, this should be minus qb, this is minus qb. So minus qb equals to this much. So when we simplify it, we get the value as q4 minus q1 minus q2 minus q3 divided by 2, that is minus qb equals to. Now notice again that on this right, on the first plate, what we have, the small q was the charge which was initially given to it, that is q1 on the plate 1, and all the other charges were subtracted divided by 2. Similarly, on this fourth plate, the charge appearing on its left side is the charge which was initially given to it minus all the charges divided by 2. Now this, you don't have to remember these formulas. This is just an observation you can use while you are calculating or using it in a problem. But I will again repeat that you don't have to remember these things. The only thing that has to be remembered is that the net charge on the extreme left and on its left face and net charge on extreme right on its right face is same, and that equals to sum of all charges divided by 2. This calculation is just for the sake of completeness. Similarly, we can calculate q2 plus q, that is equals to qa, and that equals to q2 plus q, and we substitute the value of small q, we obtain this result. Finally, this qa is q1 plus q2 minus q3 minus q4 divided by 2. So in sum total, I have calculated charges which are appearing on each faces on this conductor. The point to be remembered is the charge which is appearing on extreme left on its left face and on extreme right on its right face is same, and it is sum of all the charges divided by 2. Rest charges, once this is calculated, rest all the charges can be calculated. In my next video, I will calculate the electric field between the plates, that is between plate 1 and 2, or 2 or 3, or 3 and 4, and also the potential difference between these plates. Thank you.